So good day everyone, welcome back for another video. This is ece23, Module 3 Performance Task, Introduction to Digital Communications. This is yours truly, Restart Akabal, BS ECE3C. So the topic to be discussed in this video are PWM or Pulse Width Modulation, Natural Sample PWM, NBDS, how the common mode and differential mode digital output signal are derived based on the input waveform of a NBDS. PWM or pulse width modulation. Pulse width modulation is a modulation technique that generates variable width pulses to represent the amplitude of an analog input signal. The output switching transistor is on more of the time for a high amplitude signal and off more of the time for a low amplitude signal. So we have here a example of a PWM. PWM is exactly different from PAM in that it performs sampling in times whereas PAM provides sampling in amplitude. Consequently, the information is coded into the pulse time position within each switching interval. PWM only requires synthesis of a few discrete output levels, which is easily realized by topologically simple high-efficiency switching power stages. On the other hand, the bandwidth requirements for PWM are higher than PAM. This penalty is well paid given the simplifications in the switching power supply. Natural sample PWM. Naturally sampled PWM is traditionally an analog technique where the input signal is naturally sampled by the carrier triangle waveform at the instant of the switching edge. Natural sample PWM can react instantly to changes in input and command and produce no attenuation or distortion of the synthesized waveform. Pulse width modulation is based on the simple fact that mean value of a two-level square wave is proportional to its duty cycle. Thus, any signal can be modulated as a square wave by ensuring that the duty cycle always corresponds to the signals in the instantaneous values. So we have here an example figure of pulse width modulation. NBDS or natural sampling single-sided three-level BD. NBDS is by simple superstition since NBDS can be synthesized by 180 degrees phase shift of the modulating signal to the opposing modulator. Natural sampling refers to the amplitude representation in the modulation. Quite simply, analog signal results in natural sampling. Single-sided can be performed with ascending or descending sawtooth carriers. So we have here a figure example of NBDS pulse width modulation. So we have A side, B side, differential mode, and common mode. To get how the digital signal of A side, we have here a sawtooth wave and a sine wave. So at this period, we have positive 1 because we have here the our sine wave is greater than our sawtooth wave. So we have 1. At this period, our sine wave is less than our sawtooth wave. So we have a value of 0. Next, we have our sine wave at this area is greater than sawtooth wave. So we have a value of 1 and continues to the end of the digital signal. At B side, we have here sine wave. We have here a sine wave and a sawtooth wave. At this period, we have value of positive 1 because our sine wave is greater than our sawtooth wave. At this period, we have a value of 0 because our sine wave is less than horizontal wave, and continue to the end of the digital signal. So differential. So B side are no longer the simple complement of A side. Instead, the B side are driven by a modulator driver derived from an inverted version of the audio signal. B side switching node waveform is inverted in time within the sampling period with respect to the A side waveform. So our B side is an inverted in time within the sampling period with respect to A mode. So we have seen here, uh, it is not an ordinary complement of A side. It is inverted within the sampling period with respect to the A, inverted in time within the sampling period with respect to the A side waveform. Differential mode. Signal flows on opposite direction in pair of a line. Common mode. Signal flows the same direction in pair of lines. Using both references, signal its inverted or uninverted carrier signal, separate comparisons are made for the A side and B side signal respectively, resulting in three possible output signals. The differential output signal is a pulse train with the same polarity as the audio signal and a zero differential output. You have a zero differential output. Then the reference signal is zero. The common mode signal of two modulation signal is not zero as for the two-level modulated example since the two comparisons are modulated at different times. NBDS is seen to have severe common mode components around all harmonics of the switching frequency. In class BD, since the two legs of the H bridge do not exactly complement each other, the signal across the load, which is developed by the voltage at the A switching node minus the voltage at the B switching node, does not simply switch between the two supplies. Result, there is a third state zero differential voltage established when both switching nodes are at the same potential. One immediate effect of this is that a class BD has a significant common mode component. Class BD also requires more precise switching control and can introduce adoption complexity. So, and that's all. Thank you. So, we have discussed um, so in summarization, we have discussed the PWM, pulse width modulation, natural sample PWM and NBDS are and how the common mode and differential mode digital output signal are derived based on the input waveform. So that's all for this video and thank you.